Hi, my name is Angel Patino, and today we're going to be talking about Parseval's relation for aperiodic signals. If x of n and x of e to the j omega are a discrete time Fourier transform pair, then we have this equation. This is Parseval's relation for the discrete time Fourier transform. On the left-hand side, we have the total energy in the signal x of n, and Parseval's relation states that this energy is equivalent to the integral of the energy per unit frequency over a period of 2 pi. We refer to the modulus of the discrete time Fourier transform squared as the energy density spectrum of the signal. And the main idea of Parseval's relation is that the average power in a signal is equivalent to the sum of the average powers of each individual harmonic component. So next we can detail a proof of this. So if we start with the right-hand side, we can use the definition of the discrete time Fourier transform and the fact that the modulus of a number squared is equal to itself times its complex conjugate, and this is shown in my accompanying work. So that's how we get the second line. On the third line, we just move terms over such that we can integrate over the exponent alone. So that integral 1 over 2 pi times 1 over 2 pi is effectively delta of n minus m. You can pause and look at my proof down here. And so if we take that to be delta of n minus m, if we multiply that times x conjugate of m, we effectively get x of n. So the summations are equivalent. And since x of n is multiplied times its conjugate, we're going to get the modulus again. And so that's how we come about with that equation. So in this class, it's important to know that if you know the discrete time Fourier transform of a signal, you can often use the properties to simplify your work. And to illustrate this idea, I will have an example. So consider the signal x of n is equal to 1/4 u of n. So, and you're asked to compute the energy of the input signal. So immediately we apply the discrete time, the Parseval's relation, and plug in the discrete time Fourier transform pair. You can apply the modulus to the top and the bottom. So on the top you get 1, and at the bottom you get that. And the bottom you can multiply by the complex conjugate. That simplifies to 17 over 16 minus cosine of omega over 2. That integral from negative pi over pi, you can trust me, is going to be 32 pi over 15. Multiplied by 1 over 2 pi, you get 16 over 15. And if you want to check your work, you can simply apply the geometric series. And so it shows that Parseval's relation does hold and these are equal. And that's a good place to stop.